Hello everyone, my name is Yang Liu. Today, let's explore the fascinating world of trigonometry by diving into its history, practical applications, and artistic beauty. Have you ever wondered about the angle of the Leaning Tower of Pisa? With the help of trigonometry, we can solve such mysteries. Today, our focus will be on trigonometry's history, its functions and graph, and its artistic expressions. To start, let's dive into the origin and evolution of trigonometry. The history of trigonometry spans thousands of years, beginning in ancient Egypt and Babylon, where geometry served practical purpose. By the 2nd centuries, Hippocrates introduced the first trigonometrical table. Indian mathematicians like Arya Porter refined sine functions, where scholars of the Islamic Golden Age introduced tangent and cotangent functions, advancing the field further. By the 15th century, Europe applied trigonometry to navigation and astronomy, with in the 18th century defining its model form. Today, trigonometry has become a universal mathematical language. Now, let's explore the second section, the functions and their graphs. For precise visualization, I create all the diagrams in this presentation using GeoGebra. First, let's take a look at the definitions of sine and cosine. Building on the sine and cosine definitions in a right-angle triangle, we extend this to the unit circle. Here, a right triangle with radian 1 allows us to define point B coordinates as cosine theta and sine theta. If point B moves diametrically, its coordinate formula remains unchanged as B of cosine theta and sine theta. Additionally, using the definition of circle, we derive the fundamental formula cosine square theta plus sine square theta equal r square, which equal 1. Next, we plot trigonometric functions to visualize how x and y vary. We can observe that the period of trigonometric functions corresponds to a full circle, which is 2 pi. Additionally, we can identify some special angles from the graph. From the sine and cosine graph, both have a mass of 1 and a mean of -1. Using this, we also draw key identities. Moreover, we explore other important trigonometry identities as follows. Let's look at two variations of sin x. The first completes one period faster, where the second has an amplitude that is double. The same pattern applies to similar variations of cosine x. To conclude, the parameters A controls the amplitude, where B determines the frequency. In addition to sine and cosine functions, there are other common trigonometrical functions that can be derived from them. Now, let's return to our initial question. What is the angle of the Leaning Tower of Pisa? Using trigonometry, we determined that its angle was nearly 5.5 degrees. Trigonometry functions play a crucial role in astronomy, especially in calculating celestial distance and position. Using formula like the cosine laws, we determine angular heights, where the parallel distance formula allows us to measure the distance to nearby star. Additionally, the orbit mechanic formula describes the elliptic orbits of planets. These equations highlight how trigonometry helps us explore and understand the universe's vast structure. Next, we move to an exciting section, exploring the artistic side of trigonometry. Before we begin, let's introduce a concept. This is a Cartesian coordinate system, the most commonly used one. But as there are other coordinate systems, the answer is yes. One such system is the polar coordinate system. Polar coordinates have a rich story, from Apollonius and Ptolemy describing celestial paths to Newton's application in orbital mechanics. formalized them in the 18th century, linking polar and Cartesian coordinates with key equations. This made polar coordinates essential in geometry, physics, and engineering. In the Cartesian coordinate system, coordinates x, y can also be represented in polar coordinates as r, theta. As shown in the presentation, this method is intuitive for describing circular or rotational patterns. Let's examine the parametric polynomials, a curve that merges mathematical precision with natural beauty. Let's explore the fascinating parametric polynomials function. So polar to custom conversions, periodics, and intradates pattern offload as theta varies. The parameter k determines the number and the symmetry of petals. Integral values of k produce 2k petals, while fractions or irrational number creates intricate open pattern. This interaction between sine and cosine mirror natural symmetry, like flower petal, its periodicity not only holds expected value, but also has practical use in analyzing waveform and vibrations, describing phenomena like mechanical oscillations, light, and sound. Additionally, parametric formula like these are widely used in computer graphs for creating visually striking animation. The parametric polynomials graph usually represents signal periodicity and symmetry. In AM signal, pitch change the level frequency shift, while in FM, pitch number indicates modulation dips. In 5G network, MIMO antennas utilize high directionality to reduce interference. Adjusting the Rhodes graph parameter help visualize the distribution of male directional beams, assisting in antenna design. In conclusion, we explored trigonometry functions and the parametric polynomials, examining their historical roots, concept, and real-world application. Remember the beauty found in the study of the math. Exploring these concepts enhance our grasp of mathematical concept and reveal the intelligent connection between math and nature. This interdisciplinary view offers a new appreciation of the harmony between mathematics and the natural world.